Yes.
Okay.
No,
Thank you very much. Yeah, thank you very much, Vasko, for your kind introduction. And as you announced, this is a talk on history of gas discharge physics. And of course, this is more a kind of entertainment. I want to show you a few colored picture, but maybe in the early morning, this is a good idea. Of course, the history of gas discharge physics is so large, so huge, that I can only catch a few aspects and show you a few points. And maybe others of you, like Zoran and others, they know much more about that, or maybe they can add. And of course, by far, this will be not complete, this overview. I will touch the very early days of gas discharge physics, maybe a little bit, and show a few highlights. And I will illustrate a few of the points with some experiments we made here in our lab. And I prepared a few movies, and I hope you can see that. Of course, where's Kiel, you may ask, and a few of you may know it. Kiel is in the very north of Germany at the Baltic Sea, and especially in summer, it's a nice region for sailing. This is here the Baltic Sea, and this is the fjord, and here on the western part of the fjord is our university located. And in principle, one could sail from Kiel to Sosopol maybe for the next flight, along Netherlands, along France, along Portugal, Italy, and Greece, and come finally to Sosopol. And this is nice to remember our place in Sosopol. Hopefully we can be there the next time. And again, here, this was 2017, and the last time in 2019, together with me, there were also Victor, who will give a talk tomorrow, and Julia. And I show Julia here because she did a lot of these studies. She wrote a bachelor thesis on history of gas discharge physics, and together we prepared a few of these materials. So I will shortly touch the very early days where nobody knows about plasmas and gas discharges, and the men, they try to explain it just by mythology. And then I will give a few highlights from the 18th, 19th, and 20th century. Okay, let's start. Of course, one of the most prominent plasmas is our sun. This is the plasma for our life. And we know that if we observe the sun in sunset, that the shape and the color of the sun is changing, but this is nothing related to the sun itself. It's just related to the refraction and diffraction of light if it is crossing through our atmosphere. But in the sun itself, sorry, it's in German, we can find many, many different kinds of plasmas. In the core, we have the very hot fusion plasma, where the hydrogen is formed to helium, and the energy is released and transported through the radiation zone and the convection zone, also very interesting kind of plasmas. And at the surface of the sun, we have the photosphere, and finally the chromosphere and the corona. All these different parts of the sun are plasma topics with different temperatures and interesting properties. So this kind of plasma, the sun, is necessary and very important for all of us. We get the light and the energy from that. And the idea is to have such a sun also in the lab for energy production. And you know all these challenges all over the world in fusion research. If we plot here the temperature which is reached in the fusion devices, in the lab devices, and here the so-called triple product or fusion product. So the problem is not in the lab to reach the high temperatures, and also not the density. The problem is the trapping time, to realize the long trapping time. And our sun would be in this diagram somewhere here on the top. So it's not that hot, but of course, there's a large triple product, large fusion product for fusion. And that would be nice. And here's the ITER. Maybe in a few years, we will have the ITER and we can demonstrate, or the scientists can demonstrate by ITER that we reach the breakdown. So this is the idea, to use one of the natural plasmas, the sun. And the other natural plasmas on Earth, they have not so much natural plasmas, more in the lab, artificial plasmas, but the natural plasmas, of course, as you know, are the northern lights or the auroras and the thunderstorms, the lightnings in thunderstorms. And also from the lightning, from the thunderstorms, probably the man took the fire. And the fire you can regard, if you want, as a special kind of plasma, which is used since the early days of mankind. And you can see if you change the gas, here this is the flame of for the gas blower, and if you change the gas, if you add oxygen, you can change the shape, you can change the color, and even here a very simple experiment, if you put just a little salt into the flame, then you can see that it will be bright in an orange light, as you can see here. You can do this experiment at home. And this is the early days of spectroscopy, of optical spectroscopy. And here again, a few pictures of lightnings, of thunderstorms. And of course, the people in former times, they worried about that. They had no real explanation on the nature of thunderstorms. And nowadays we know that thunderstorms don't occur only in the atmosphere, but also above the troposphere. We can find bolts, we can find thunderstorms as seen by airplanes or by the International Space Station. And of course, there are two conductive sheaths or another conductive sheath, the ionosphere, and so we can even have thunderstorms above the troposphere. Or also in clouds of a volcano, and this is a kind of dusty plasma, of course. We have charge, dividing of charges, and very strong electric fields can be produced in such volcanic ash clouds of volcanoes, where you can also observe these thunderstorms. And this was, there were no explanation in the ancient times, and so of course the gods, they had to explain these effects, these observations. And if you look for the Greek mythology, you can see often that Zeus, the main god of the Greeks, the godfather, he has lightning. He's a pitcher of thunderbolts, and he rules the life, and he can punish by lightnings or by thunderstorms. Also in the Nordic mythology, we have the northern god Donar. He's the god of thunder, and the people in the north, in Scandinavia, they assume that Thor or Donar, he works with his hammer as a smith, and the sparks produced are scattered over the sky, and this is the thunderbolt. Okay, and the Greeks, they tried already to give a scientific explanation. For instance, Democritus, he said these thunderbolts may be atoms of fire. He was the father of the atom theory, and Aristotle, he assumed that these lightnings are vapors of sulfur. Okay, but that is not a real science, and the real science in plasma or gas discharge physics maybe started in the 18th century. And there were observations, and I hope you can see this video, already by Torricelli, by Picard, by Bernoulli and others. if they operated their tubes for pressure measurement, just the U-tubes for barometric measurements. And if they operated with these tubes in the dark, they observed some light in these tubes due to the mercury vapor. And this is just, as you have seen here, if I shake, this is the glass tube with some mercury in it. And if I shake this tube, you can see in the dark, there is some light. I introduced here some neon or nitrogen, so you can see this in the dark. And also Torricelli and Picard, they observed these effects. This is, of course, by friction or by triboelectricity. And this was the source in the beginning of the experiments in gas discharges. And we have to mention Francis Hawksby in England. And he published in 1709 a book, Physiomechanical Experiments on Various Subjects Touching Light and Electricity. So these are a few illustrations from his books, and he could already evacuate a glass tube and with some mercury inside, and then this by the frictional operation, so triboelectricity, he could observe light in this tube. And this was maybe these investigations, they led later to the development of gas discharge lamps. And the reason is triboelectricity or frictional electricity, as I mentioned, as you can observe it in the Van de Graaff generator. If you charge up, then you have here the electric field, and you can see by these bands, you can see the radial structure of the electric field. And a very simple experiment is my granddaughter, if she's going down here the slide, it's charged up, and you can see here also the radial structure of the electric field. And in each school and university in the first year, you have this experiment, and this was a very important invention, the electric machine or the influence machine, how is it called, also by friction, and it can be amplified by the influence. You can collect a lot of charges on these tips, and if the charge and the electric field is large enough, there is a breakthrough. You have a small thunderstorm, a small lightning in between, you can see the spark. And that were the experiments used in the former or early days of gas discharge physics. You can add a lot of these slides in an influence machine, as for instance, Wilhelm Holtz did, end of the 19th century, here in Greifswald, here with additional Leyden jars. And so you can create very large charges and strong electric fields, and you can study the breakthrough, which is typically for dry air in the range of a few tenths of kilovolt per centimeter. And I did once such an experiment, as you can see here. This is the influence machine, and here the sparks are formed, and please look what happened. Look, that was not a nice experience. You can do something wrong, but what you can see here is that you really can observe the sparks between the tips of these machines. But coming back to Francis Hawksby, and he did these experiments. And if you have the chance to go to Glasgow, to the University of Glasgow, in the library, there they have the original books and figures here of the work of Francis Hawksby. But the problem was they could, by these experiments, they could create sparks and short discharges, but they could not save the electricity for a longer time. And that was important that Peter van Musschenbroek, a Dutch physicist, he invented this called Leyden jar, where he could store, he told he could store the electricity. And these, what we know nowadays, capacitors, here there are 2 electrodes, and in between the dielectric, they were formed as bottles or as jars, therefore Leyden jars. It's interesting that a few years before, I mentioned that here there was Ewald van Kleist, and he was in Pomerania in the northeast of Germany. He was a priest in a monastery, and he invented the so-called Kleistsche Flaschen, the bottles of Kleist, but he never published that in a scientific journal like Peter van Mussenbroek. And only 1 or 2 years later, he published his inventions on the Leyden jars. And these jars have been used later by Franklin, by Lichtenberg, and others for their experiments. Here's another picture of the book of van Mussenbroek, where he described the first Leyden jars. And then a few years later, end of the 18th century, Benjamin Franklin we have to mention, of course. Franklin, he did his very famous and well-known experiments, and he invented probably the lightning rod, which can protect the man and houses and other stuff for lightning, for the thunderstorms. And if you look to his paintings or his drawings, he described the construction of these rods and how to protect, how to use these rods for protecting. Also, the books and the descriptions you can find, for example, in the Library of Glasgow. But Franklin, he was not only an inventor of the lightning rod, he was also a statesman, a philosopher, and as you know, and he was one of the fathers of the United States in that time. And he did experiments similar to that of Dalibard, who did it in the same time. And they have experiments like here. They had a little house of wood and then a long antenna, a metallic rod. And they tried to attract, if there's a thunderstorm coming, then they tried to attract the lightning to the tip of the rod in order to collect a huge flux of charges, huge currents for experiments here in the house on an isolated table. And you see in the books or the paintings here, Franklin with his son, he made experiments with a kite. So they really they moved the kite into the thunder clouds. And this is really a nightmare, terrible to see these pictures today. And it's really a wonder, a huge wonder that nothing happens. But that was the source to collect from the thunder clouds, to collect a huge amount of charges for their experiments. At the same time, in Russia, Lomonosov made also such experiments with his assistant Richman. He was a German, and maybe or probably Richman was the first victim of physical experiments. And he really, as you can see here, hopefully, he died in such a very dangerous experiment, as I explained shortly, by these experiments with the current through the rods in the lab. And this picture here shows this terrible accident. And there was a philosopher and scientist in Germany, in Leipzig, Johannes Winkler. He's not well known, but he wrote a book in 1746 in German, Die Stärke der elektrischen Kraft. That means the strength of electrical power. And he wrote the following sentence: "It seems that the electric sparks, which have been artificially created, is in matter and in principle and in generation closely related to the thunderbolts, and the differences are only in strength and weakness of their effects." And so this is a correct explanation. What we see in the clouds, in the thunderbolts, the discharges, and the name discharge is coming from that. We have a charge a huge charge, and suddenly, if the field is strong enough, depending on temperature, humidity, and so on, then you have the discharge. And what they observed, the sparks in lab by triboelectricity, or if you store the electricity in, or the charges in the Leyden jar, then you can have also huge sparks. And this is the nature is the same as in the thunderstorms. I go back to Great Britain. At that time, Joseph Priestley, he was a theologian, also a priest, but also a nature scientist, and he was observing very carefully the nature. And he was also a member of the Royal Society at that time. And he wrote a very interesting book in 1767, The History and Present State of Electricity. In the former times, all the inventions and the observations of gas discharges are related to electricity, to the story of electricity, of course. And he constructed already an electrical machine and discharge and investigated what we would call arc discharges, and also he observed sputtering. So he had a battery, a large battery of Leyden jars, so where he could store a very large amount of charges, and then he observed the sparks and later also arcs between the electrodes. And in this book, he also described that he could observe the position of metals from the electrode. So this is due to corrosion and sputtering, of course. So in principle, he observed cathodic arc coating in air, and he could also see that the deposited film on glass, he did on glass, was very well adherent for thin films, and that is what we are using nowadays for thin film deposition in optics, in microelectronics, in tribo deposition, and so on. In the same century or decades, Georg Christoph Lichtenberg, he was in Göttingen, and probably he was one of the first what we would call physics professors in Germany. And he was also studying some things based on Franklin's lightning rods. He brought it in principle to Germany. And what is important, he could observe by applying a high voltage to an insulating material as glass, and then by sparkling its surface with sulfur or lead powder, he noticed these characteristic patterns, the so-called Lichtenberg figures. As you know, these fractal structure of the Lichtenberg figures are very interesting for topology, but they can be produced very easily by discharges. Here are a few pictures from his book. And if we have such a discharge, here's the rod, it's the electrode, and here's a dielectric plate with some powder. You can see how these figures, Lichtenberg figures, are produced. I go back to the 19th century, and we begin in the beginning of the 19th century with a Russian scientist. He was also a member of the Academy of Science in Russia, Vasily Petrov. Petrov is very well known. He reported in a book announcement on galvanovoltaic experiments, and he described clearly the first continuous arc discharge. He really constructed a very huge battery for having high current for these arc discharges, and he observed melting, burning, and erosion of the metal. So he was the pioneer of arc discharges, and at the same time, Humphrey Davy in England, he also observed, did such experiments with huge batteries, but he was not, he was unaware of Petrov's work in Russia, because Petrov, he published in Russian, and Davy was unaware about that. And the same year, or maybe 1 year later, he did very similar experiments on continuous arcs. And also he invented the so-called Davy lamp, which has been used in that time as a safe lamp for workers in the coal mines. And also he made public outreach, public discussions. And so you can see here's a lecture hall with Humphrey Davy, and in the basement beneath the lecture hall is a huge battery of for the high to have the high currents. And so he could illuminate by arc lamps, what we would call today carbon arc lamps at atmospheric pressure. He could really illuminate this lecture hall. You see here the shadow, the sharp shadow in the night, and it was bright as a sunny day. That was very impressive. And then Michael Faraday, he was an assistant of Davy, and of course all we know Faraday, and he did a lot of investigations also in discharge phenomena and electric currents in diluted gases. He described correctly the pre-ionization, and also a few parts of a column in a discharge between cathode and anode is named after Faraday, the so-called Faraday dark space. As you can see here in this experiment, this is just a neon discharge tube, and you can see the positive column. Here's the anode, here's the cathode, and here you can see the dark space. This is not the Faraday dark space. The Faraday dark space would be here. This is the Hittorf or Crookes dark space. And he wrote in his experimental investigations that that form of the gas discharges, which appears as a glow, is very peculiar and beautiful. And the dilution of the air enhances wonderfully the glow phenomenon. He really described these nice glow phenomena in the discharge tube. And he also explained already the creation or the formation of sparks, as we can observe in these influence machines. Here you can see. And for instance, if you change the distance between the electrodes, then you need a much higher voltage for the creation of the spark. And there is a proportionality of the distance, the voltage, and that's the electric field, of course, the ratio between the voltage which is necessary for the spark and the distance. And he also described that the first spark is the most difficult. It needs the highest voltage for the first spark, and for the second, third, and so on. And here for the 10th spark, you need only less voltage. Here it's maybe about 2 kilovolt. Here you need more than 3 kilovolt for our experiment. We did this in a bachelor thesis. And this, of course, the first sparks, there is some UV light. There's already a production of charge carriers in the air, in the gas. And so you have pre-ionization, and the next discharges, they are easier or the next breakthrough is easier to attain. This is already described, has been described by Faraday. And he also mentioned or observed that the breakthrough is dependent on the gas. If you take air, wet air, dry air, hot air, or if you take other gases between the electrodes that he could describe. And we know, of course, now later Paschen explained in his Paschen's law that the minimum for the breakthrough or for the breakdown voltage depends, of course, on the gas. That means on the electronegativity or the depending states of the gas. And that has already been observed by Faraday, but Paschen explained this in more detail. And another interesting experiment by Faraday was, of course, he was in principle the inventor of the electromotor. He called it the philosophical motor. It's Faraday's philosophical motor. He was mercury in this groove, and then there was a current through this device to this wire and back. And if he inserted a magnet, it starts to rotate. That's the principle of the Faraday motor, of course. And we did such an experiment in a plasma. As you can see here, we have not a metallic wire, but we have a plasma wire. It's a constricted discharge. Here's the anode, here's the cathode, and this is the example for the symbol of our working group. And you can see here this nice experiment in a video. I hope at least you can see that. Here's the cathode, here's the anode. Here we have the constricted discharge. This is the wire, and it would be the mercury growth. And if you insert now a magnet, you can see what you would expect. The wire, the plasma wire starts to rotate due to the Lorentz force. Even we can improve this experiment. We have here a discharge tube. There is an inner tube and an outer tube, and only the space between is evacuated. And now we have a constricted discharge. It's an argon. You can see there's some convection. The discharge moves to the top. And now I insert a magnet, and you can see here, this is really wonderful, like a metallic spiral. It starts to produce a spiral. You can even observe dispersion relations in these things. And if you change the polarity of the magnetic field, there's turning to the other side. And this is the interaction between plasma and magnetic fields, between the charge carriers and the plasma and magnetic fields. And this was also interesting for Gauss, Carl Friedrich Gauss in Göttingen. And he was observing the Earth's magnetic field. He did a lot of nice inventions and observations. And he correctly stated that the fluctuations in the magnetic field of the Earth were a consequence of electrical discharge happening in the conductive layer of the atmosphere. And also the existence of the aurora borealis, of the northern light, could be explained by this idea, because there is a flux of charge carriers coming from the sun, from the solar wind, and they are confined near the polar regions due to the strong the strong magnetic field. And if they move, they spiral along the magnetic fields to the deeper layers of the atmosphere, and then we have collisions with the energetic charge carriers, with the nitrogen or oxygen in the atmosphere, and so the polar lights are formed. And this is related to the magnetic field, as you have seen here in our nice experiments, the interaction of a constricted plasma wire with a magnetic field. You can see a few nice pictures. You don't have to go to Scandinavia like here, even sometimes in Germany and north of Germany, or even in Italy sometimes, if there are strong storms, solar wind, you can observe polar lights also in Middle Europe. And then there are two schools that came up, the German and the British school of gas discharge physics in the 19th century. And the father of the German was Julius Plücker in Bonn. He observed electrical discharges like Faraday, and he made studies on spectra, which has been used later by Balmer and others. But he could also do his nice experiments based on Faraday's idea if he had very good discharge tubes. And at that time, there was a German glassblower. It was Heinrich Geissler. He was really a gifted craftsman, and he invented the mercury pumps, and he improved significantly the vacuum pumps and the vessels. And so by the so-called Geissler tubes, they could observe the luminosity of materials in the screen, the fluorescence, and that was due to the bombardment of electrons. So they could produce electrons in an electrode which are accelerated. And if you fill these tubes with gas, then you have, of course, the collisions of the electrons, inelastic collisions with the gas, and you can produce nice discharges. As one of the scholars of Plücker, that was Theodor Meyer, he wrote down in 1856 in a book here observations of striated electric light. And he plotted wonderful colored pictures in his book, depending on the gas and depending on the electric field. He could observe homogeneous or striated discharges. We did this also in an experiment. I hope you can see this is a discharge tube again with a different diameter, and we can obtain these discharges, and the distance between the striations depends on the diameter of the tube. So there's an interaction between the floating potential of the inner of the tube and the plasma potential in the center of the discharge. It's a surface to volume effect. So the distance between the striations depends on the geometry of the tube. And there's electric field, a weak electric field between the striations. You can see that, or we observed that by putting some powder particles, injected powder particles into this discharge, and they are illuminated here by a laser. And you can see they float between the striations, and they are charged, and the gravity is in this direction, and the electric field is in another direction. And so there's a balance between the gravity and the field, and the particles can float here in the discharge. Another scholar of Plücker was Johann Wilhelm Hittorf, and he already made some measurements of potential distribution and current flows. He put different wires into a discharge tube. That was what we would call nowadays the probes, the Langmuir probes, and he could measure already, or got some information about the potential distribution and the field distribution in such discharges. And what is also interesting for the Paschen law, he demonstrated qualitatively by a nice experiment the Paschen law, the so-called Hittorfsche Umwegröhre, maybe in English a detour discharge tube. Here is a tube with a long way and with a short way. Here are the electrodes. I'm not sure if you can see it. Here are two electrodes. And if the pressure is high, then the discharge is here at a short way between the electrodes. But if the pressure is low, then there's a detour of the discharge. The discharge is going the long way. And this is a nice illustration of the Paschen law. A few years later, Eugen Goldstein, he observed the cathode rays. Nowadays, we know it's the electron rays, of course, and the so-called canal rays, which are the ionic part, or the ion beams. So the cathodic rays are only dependent on the electrode material, not on the gas, but the canal rays, the ion beams depend, of course, on the filling of the discharge tube of the gas. That was a German school, and simultaneously in Great Britain there was the school established by Crookes, and he also predicted that the cathode rays must be an amount of negative charge particles from the cathode independent on the gas. And he called these discharges already the fourth state of matter. You can see here the fluorescence tubes by Crookes due to the electrode rays or electrode beams. The fluorescence is excited, as you can see here, and also the parts in a typical discharge tube. We discussed already the Faraday dark space, but here the cathode fall in the DC discharge, the dark space in front of the cathode is also called the Hittorf or the Crookes dark space nowadays. Then from that school, Thomson was he observed, or he found the electron just by these experiments by Crookes and his scholars. I skipped this. And maybe I should shortly mention, of course, Tesla and Zoran could give an extra lecture, of course, on Nikola Tesla. But what is important, he was not only a scientist, he was also a founder of many of companies and a businessman. And he patented in 1991 the Tesla coil, which was a high-frequency transformer to generate impressive discharges around high voltage terminals. And he was dreaming about sending energy by waves without wires. And nowadays we know Here's a picture of Nikola Tesla in front of if you go to the Niagara Falls in the US, there is a water power station, and in front of this water power station, you can see Nikola Tesla. And what I want to tell you with the beams, with the electromagnetic waves, Tesla was dreaming of, that's realized, for instance, in microwave discharges. Yeah, this is just a microwave oven in the kitchen, and we have just a glass sphere filled with argon or with nitrogen, and without electrodes, and the electrons which are in the atmosphere are accelerated, and by inelastic collisions, these particles collide with the gas atoms or molecules in order to excite and to ionize. I will come at the end to the 20th century. I will still mention a few names you know very well, of course. Peter Debye, he was studying at first a lot of effects in electrolytes, and in a certain sense, the plasma and the mixtures are the charges in the plasma are very similar to electrolytes, and many names in plasma physics, like the Debye length, the Debye shielding, or the Debye sphere, was called after him. And Child, he investigated in very detail the correlation between the voltage and the current among two electrodes in vacuum, and he refers that the limitations of the currents in the plasma are due to the space charges in the cathode fall or in front of the electrode. And this Child-Langmuir law, which we are using nowadays, this is the Child-Langmuir law, as you know, for the collisionless case. There are also equations for the collisional case, but this is very important to investigate and to describe and to scale up discharges. Townsend, he published a lot of papers, and what is very important is that he clearly described the acceleration of electrons in an electric field, which can generate new electrons by inelastic collisions with the gas atoms, and this is described by the first or by the Townsend ionization coefficients, as you know. That was also in Oxford. And the last name I want to mention is Erwin Langmuir, who introduced the word plasma, but he did much more in plasma physics. I refer to the Langmuir probes, I refer to the Langmuir waves, and so on. So I would coming to an end, and the word of plasma, Levi-Tonks, later in the 60s, he remembered his meeting with Langmuir, and in 1928, once Langmuir entered the lab, and he was looking for a name for this, and he took the name plasma, probably from the blood plasma. Okay, if you are interested in more information, I could send you a list of references of literature, and I have to thank especially my former teachers, Alfred Rutscher and Hans Deutsch in Germany. Alfred Rutscher, he died already, unfortunately. Hans Deutsch, he's still in Greifswald, and Gerrit Kosen in Eindhoven, and of course our student, master student Julia Cipo and Silvio Krüger and Yen, who helped in taking these videos and the experiments in the lab. The last word is the history of gas discharges in Kiel. There were a few well-known names: Heinrich Hertz, Philipp Lenard, Max Planck, and Albrecht Unsold, all known in plasma physics. They started in gas discharge physics, but later they did astronomy, astrophysics, or the electromagnetic waves, or the father of the quantum theory, of course. If you want to know much more about that, just go to our homepage. You can find the timeline of the gas discharge physics and some posters with these names, with more information, as I mentioned, and you can simply download this from our homepage. So with the last pictures here, our nice remembering for the VEIT in Nessebar or in Sosopol. I hope we can meet again the next time and dancing at the VEIT in Sosopol. Thank you very much for the organization and for the possibility to give this talk.